So let's go on what we have begun last time, so during the last video. So we were exploring the direct isometries, and so we found out that knowing that the matrix would be written like this, the corresponding eigenvalue would be those ones. Let's rewrite them a bit more in a nicer way. Minus b. Sorry, we have a plus here. So, 2 cosine theta over 2, that's cosine theta, plus 2I sine theta, that's going to be I sine theta. So actually I can rewrite that lambda 1 is going to be EI theta, and lambda 2, well, you remember that's a property of polynomials. When you've got a complex root, it doesn't come alone, it always comes by pair and they are conjugate. And so that I get the second one is cosine theta minus I sine theta, that's E minus I theta. Okay, so I've got those two complex eigenvalues, and unless theta, so it's going to be real eigenvalues if theta is equal to 0, not theta, to 0, and in that case we get that m is actually the identity, and other case when theta is equal to pi, and in that case m is equal to minus the identity, and otherwise complex eigenvalue. Okay, and the product of these eigenvalues is of course equal to 1, so that you get a determinant of 1 and you get this direct isometry. And so let's understand what it corresponds to. Right, if I've got my complex eigenvalues, all right, so let's assume that theta is different from 0 pi. What does our matrix mean? If I rewrite my matrix like this, cosine theta minus sinus of theta, sinus of theta, cosine theta. What does this correspond to? That is, if you denote E1, the unit vector 1, 0, and E2, the unit vector 0, 1, they make the standard orthonormal basis of R2. So this corresponds to f of E1, and this corresponds to f of E2. Okay, well, f of whatever is the matrix M times the vector. Okay, the map that it represents. So let's try to understand what it means. It meant that okay, I'm in R2, and I've got my E1 vector and my E2 vector, and let's see where this is sent. Let's take theta is a nice angle. Let's check that this is theta. So instead of 1, 0, f of E1 is going to be sent to cosine theta, sine theta. What does it mean? What's this vector? That's the vector with coordinates cosine theta, sine theta. Okay, it corresponds exactly to this point where you take the point on the unit circle that corresponds to the angle theta, and that's the corresponding vector that you get. And maybe you remember that from last year's parametric curve chapter, you had to consider this vector when you were doing some local study. But anyway, right, so that sends the E1 vector here, and that sends the E2 vector, well, the corresponding one is going to be, well, here. All right, if you compute the vector with coordinates minus sine theta and cosine theta, that gives you the orthogonal vector to this one, of course, because if you take that product of those two columns, it's giving you 0, which we already knew because we've got an orthogonal matrix, okay? And that gives you the image of your second vector. Okay, so what have we done here? We've really performed a rotation of angle pi. That's what we have. When we've got a direct isometry in R2, that is not the trivial I or minus I, that corresponds to a rotation. Okay, and how can we find the corresponding rotation angle? Well, simply by identifying what theta corresponds to the values that we have here. Okay, All right, so that was the direct case. Let's study what we have in the indirect case. Well, actually, it's going to be faster. Guess what? So let's see what is the matrix we get in the indirect isometry. Okay, so in the indirect isometry, we get the cosine theta, we get the plus sine theta, and the minus cosine here. And we get the sinus of theta here, so that the determinant is -1. So again, you get that you're looking for the eigenvalues, all right, and the eigenvalues are going, well, it's the characteristic equation is going to be cosine theta minus lambda minus cosine theta minus lambda plus sine theta square, and you expand that, and actually you find that it's lambda square minus 1. Pause the video maybe and do this, be sure you know. And so what do we have? In that case, we only have real eigenvalues possibilities, right? So lambda is equal to +1 and lambda is equal to -1. These are the two roots of this equation. All right, real eigenvalues here. So what does it mean? You already know actually what it means. It corresponds, you know that if you find the in an adapted basis, okay, you know, well, you can diagonalize this matrix and it's going to look like this. The diagonal corresponding matrix to this one is going to be that. And you already know what this is. Okay, this is going to be an orthogonal symmetry, right? That's what we studied earlier, right? That's what we studied last time. And so what do you remember how you you look for the angle of this orthogonal symmetry? You are looking for the eigenspace, the direction of the eigenspace associated to eigenvalue +1, okay, the one that doesn't move. And that's giving you something, right? That's giving you, well, that's going to give you the direction, actually. And actually, if you do that, well, you will systematically find that if you identify the theta here, the value of theta that gives you those values, you can show that the eigenspace associated to eigenvalue 1 is spanned by cosine theta over 2 sine theta over 2. Okay, and that's it. And so that, well, that's one vector. So that, well, you can try and plug that into the equation, and you see that this matrix times this vector is equal to the plus times this vector. So that's it. You know what it looks like. That's going to be f is, well, E1. That's going to be assuming that that's direction cosine theta over 2 sine theta over 2. So basically that's angle theta over 2, okay? And that corresponds to an orthogonal symmetry, okay, with respect to this line. Okay, so we're in R2, so that's going to be the orthogonal symmetry with respect to this one, x, and that's going to be m times x. Okay, good. So we have explored all the planar isometries. We will do some examples in class, and now we need to do the same thing in R3.